So, comparing the mass of an object to how much space it takes up. Density. Conceptually, this should kind of make sense. Here, I have two objects. I have a bowling ball and a soccer ball. And they're roughly the same size. They're not 100% the same size, but they're roughly the same size. But if I throw them at you, and I wouldn't do that for real, but if I were to throw these at you full speed, which one are you going to be more worried about? Well, the bowling ball. Even though it's about the same size of a soccer ball, it has a lot more mass than the soccer ball. And if I look at that comparison, if I have two objects that are the same volume, but one mass is much different than the other, I'm going to have two different densities. The object with the more mass, the more stuff in it, in that same amount of area or volume, it's going to have a greater density. Matter of fact, I don't have a pool here, but if I were to throw these into the pool right now, density has an impact on what floats and what doesn't float. And if I throw these in the pool, most likely, bowling ball would sink. Soccer ball would float. Well, think about that as we move forward with the rest of this presentation. Let me put these to the side. All right, now, finding the mass of an object is pretty easy. We generally can put it on some kind of scale to measure the mass. And again, as said before, we typically measure mass in this class in grams or kilograms. Volume can be tricky, depending if it's a physical object that we need to directly measure or if it's an odd-shaped object. If it's an object we need to directly measure, we can still do length times width times height to find the volume. And if I were to give you like a little cube of metal and I were to ask you to find the density, well, you could put it on a scale and get a measurement in grams. And then for the volume, you might have to measure each side in centimeters. We're in science class. Take that amount, do length times width times height, you'll get a volume measurement in units cubed. So if I measured in centimeters, if I take length times width times height, I would get centimeters cubed as a unit. If I were to get an odd-shaped object, well, again, finding the mass of an odd-shaped object is pretty easy. I could just put it on a scale. Now, this is a fishing weight, but it's odd-shaped. Now, actually, it's prism, so you probably could do a measurement and figure out its volume by a little math. But what if you're like, I forget the formula for whatever? Well, if that's the case, there's another way to get volume by what we call displacement. So if I take this object and I take what we call a graduated cylinder. The cylinder's smart. It graduated school. It's a dumb joke. If I take this graduated cylinder, what's special about a graduated cylinder? It's a special cylinder with markings that tell me how many milliliters a volume is, and they're configured to be correct. So I can take a starting amount of liquid, and here I'm just about at 20 milliliters. And I can hold that up. And you can see, I'll turn it around. Actually, I'm at 30 milliliters. You can see 10, 20, I'm up at 30. If I take my object and I slide it in gently, and I let it get to the bottom, you'll know I've risen to about 35 milliliters. Now, if you were here in lab, I'd make you read it a little more accurately, but so the liquid went from 30 milliliters to 35 milliliters. Well, why did the liquid rise? The liquid rose in volume because the object, that fishing sinker, was there. So that means if you went from 30 to 35 milliliters, that means that that fishing sinker must have taken up that extra 5 milliliters. This is called, it just escaped me. Wow, tip of my tongue. Archimedes' principle. If an object is complete, it has to be completely submerged. The object has to be all the way in the water. Because if the object's all the way in water, we know how much that water will rise due to that object in all. So, when you put an object in water and it's completely submerged, the change in the volume of that amount of water and the object combined is going to be the volume of the object that you put in the water. That's another way to find volume. And once we get that information, we can calculate, numerically we can calculate density. We know that if it's got a low density, it has a little bit of mass in a lot of volume. If we have a high density, it's probably a lot of mass in a smaller volume. In the beginning, I showed you a soccer ball and a bowling ball. Now those have the same volume, but they were different masses. In this scenario here, I have a cup full of popped Rice Krispies, and I have 2 metal masses. These 2 metal masses, they don't take up much space compared to this. These 2 metal masses are 150 grams. This cup of Rice Krispies, including the cup by the way, is also 150 grams. So here they're the same exact mass, but they're different volumes. This takes up much less space than this. This is much more dense, this is much less dense. And that begs the question, what weighs more, a pound of lead or a pound of feathers? It's an age-old question. What weighs more, a pound of feathers, a pound of lead? Well, the answer is they're the same weight. But sometimes people say, well, the pound of feathers is lighter, weighs less. Because you think about a feather and you think about, well, you know, they don't take up much space, or not, sorry, they don't take up, they take up a lot of space, but they're really light. So that tricks you into thinking, well, feathers are lighter. All right, again, this is our lead. It's pretty heavy, it doesn't take up much space. It's one little feather. It takes up some space, but it's very, 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 very light, not much mass. So to have a pound of feathers, well, you need a lot of them. You need a big bag of them, like a pillow, versus a pound of lead. You wouldn't need much space for a pound of lead. So keep that kind of in mind. Next lesson, we're going to actually get into numbers in the math. This is just kind of conceptual run. Before we get into the math, though, let's talk about sinking versus floating a little bit more. Sinking versus floating is all about density. It goes that if you try to put an object in an environment, and that environment's made of a material of a certain density, if that object is got a density greater than the environment, it'll sink. if that object has a density that's less than the environment, that object will float. The most common example of this, of course, is water. We know certain things sink and certain things float in water. And because of the definition of water, which I described earlier, because the mass of water was based off of the volume, more specifically a cube of 10 by 10 by 10 centimeters. Because that definition is intertwined, the density of water is 1. 1 gram per centimeter cubed, 1 gram per milliliter, or 1 kilogram per liter. They're all the same. Well, they're not the same in terms of units, but the density of water remember, a centimeter cubed is a milliliter. They are identical. But these are not identical, but if you convert, if there are 1,000 grams in a kilogram and there are 1,000 milliliters in a liter, the ratio still works out. So the density of water is 1. Now I did add a little food coloring again, but still it's just basically water. Now if I take a big piece of metal, well, this density is most likely greater than 1. Metals can have densities of 2, 3, 5, a lot more. And if I put this into the water, and I do it gently, the density is greater, so it obviously will sink. If I take a piece of wood and I put that into the water, it'll float, because the density of wood is typically less than 1. It's less than water. Even if you don't know the number, you know the wood is going to be less dense than the water, the metal is going to be more dense than the water. Now, what about a rock? If I put a rock in water, well, typically rocks in water will sink, more dense. But if I put that rock in water, it doesn't sink. It floats. It's floating because it's, I'm tricking you. It's called pumice, and for those who exfoliate and have pumice stones, you'll notice that this rock has in it trapped a lot of air pockets. And so if you have a lot of air pockets trapped in the rock, well, it's taking up this much space, but air doesn't have a lot of mass. It doesn't weigh a lot, so it's going to make this pretty light, lowering the density. And if it's less dense than the water, it'll float. This doesn't always have to be with water. It can be with other liquids. We know if you have your Italian dressing at home in the refrigerator, you have to shake it for it to mix. Why? It's made of oil and water. And the oil typically floats. The oil liquid is less dense than the water. And because your dressing at home, your Italian dressing, it's basically a water vinegar solution and then the oil part. So water and oil. We know they don't mix. Birthday balloons, helium balloons. What do we know when we let them go in the room or outside? They float. Because helium, it's a gas, we trap it in the balloon, is typically much less dense than the air around us. And so in that case, less dense material rises, the more dense would obviously fall. And there are a bunch of other examples out there, but if we come across them over the year, we'll cover them then, or hopefully you have this and it's enough to explain it to yourself. Okay? All right, we have one more lesson on density. It's about the math. Get those calculators.